Okay, at the end of the part 1 of this lecture video, we were saying to calculate the volumes of a solid of a revolution like this, we could use this cylindrical shell method. We could use sometimes like a washer method or disk method. In general, the cylindrical shell method is a little simpler algebraically. Let's see why. Just say again, we want to rotate the same region around y-axis. So the solid of a revolution will be the same, like a donut. Instead of picking up a vertical, we'll pick up a horizontal strip. Then we rotate. What do we have this time is a washer. So the washer formula, as you recall, is pi r out square r in square dy this time. Remember, horizontal strip, we have dy as the thickness basically. Alright, compare this to the shell method we got here. Alright, you can tell algebraically those two terms are more complicated than this. This is the usual square of a difference, square of difference, more algebraic work, while this is usually just product, simple product. So just generally speaking, if both can be done, if both methods can be applied, the cylindrical shell method is a little simpler. But there are cases you can only use one method. For example, if you have a graph, it's a third power that's revolved around this line, then the only method you can use is cylindrical shell method, because the washer method is impossible. The reason is you would pick up a horizontal strip to revolve, and the radius r in r out. You cannot solve this equation for x. For example, to find out the x at the left end, x at the right end, of course, is whatever number here. It's impossible to solve, to express it in the right form. And it's true too, sometimes the problem, you can only use the washer method to do it, not the cylindrical method. That's why we need to learn both. Now, to conclude this lecture, let's just see one more example where we're going to use cylindrical shell method. Okay, this time the region is bounded by y equal to x, x equal to y squared. So let's graph. Well, before we do that, let's see. Region is rotating around line x equal to 3. So I'm going to have more room for the positive side of axis, because a lot of things are going on over here. Okay, this way I have plenty of room to sketch graphs, to see the region, to label things. Alright, so let's graph. Y equal to x, straight line. A lot of the functions involved, pretty simple. x equal to y square. X equal to y square is this. But of course, the lower branch has nothing to do with our region. Okay. So again, we see a region that's revolved around, say, x equal to 3. You see, that's why I purposely left more room over here. When you're trying to set up coordinate system to graph, the beginning you may not be able to realize which part of the coordinate you need more room. You can always redo it once you realize you just don't have enough room to label things clearly to. Alright, so anyway, so this is the region revolved around line x equal to 3. Let's pick up a strip. Pick up a vertical strip. Now indicate it's at x, thickness is dx. Alright, and the revolve. So revolve the top, revolve the bottom. We see cylindrical shell, right? So volume of this one shell is 2 pi RH dx that we already determined because it's a vertical strip. Okay, so now to find explicit expression for volume of one shell, we need to figure out what to plug in for R, what to plug in for H. Let's work out on the side. R is the radius of the cross-sectional circle. Now marks the radius in the middle, not at the top, not at the bottom. Alright, so from the graph we see radius is a horizontal distance. That's going to be x at the right end minus x at the left end. Now what's x at the right from the graph? 3. What's x at the left? Well, it's the x position of the strip, that is x. Alright, so very clearly find 3 minus x to plug in for R. Then again, if you place your radius or draw your radius at the top, you could be confused. X at the left, you are going to use the graph of a parabola or actually the correct expression x, so it can be confusing. Alright, 3 minus x. Alright, next, height of the shell, h, which is seen in red here. Okay, so the height is, first of all, identify the type as a vertical, so it's YA minus YB. Those two very simple, very important distance formulas we use in each every problem. Now YA, so we need to find the Y expression for the position to plug in for YA. Now the top is on parabola x equal to y square, so it's clear this is the equation involved, but we're supposed to find expression in the form of y equal to. This is not in the right form, so we here have to solve. Solve for y. Alright, these two are equivalent. This is in the right form, this is in the wrong form. Okay, we can tell which way is the right form because this is y equal to, so the y equal to thing is the right form. So it's square root of x. YB, so what's the y expression at the bottom? B. Well, first of all, the end is on y equal to x. The graph of y equal to x. Y equal to x is the equation, the correct equation. Y equal to x happens to be in the right form too, so we just plug in y equal to x. Again, from this you can tell how we determine whether it's the right form or wrong form. Okay, with this simple little formula, we are really basically seeing the clues. Okay, so find out correct equations, correct the equation in the right forms, plug in. Now plug in square root x minus x dx. We can simplify before we add things up. Okay, so this is 3 times square root x, that's half power. 3 times x is 3x. X times half power is 3 half power. X times x is square dx. Alright, so we obtained explicit expression for volume of one shell. Now back to the strip, so we can see the region where we pick up a strip. We can see the first strip would start from x equal to 0 here. So we're going to add from 0 to this spot, and this spot is actually one very easy to figure out. X equal to y, x equal to y squared. You set them equal to each other, or you can set y equal to square x, y equal to x equal to each other. Either way, it's simple algebra. You find x equal to 1 and x equal to 0. Solve. X equal to 0 is here, x equal to 1 is here, so 0 to 1, just that. Okay, so this is how we set up definite integral that would give us volume of a solid of a revolution in this problem. The rest is a simple integration. Find the antiderivative of each. Power 1 over 1/2 plus 1, x raised to 3/2. 3 over 2 x squared, 1 over 3 over 2 plus 1. 3 over 2 plus 1 is 5 over 2. 1 over 3x to the third power. Okay, all using integral power formula. Okay, and the rest is just simple computation. Simplify the coefficients, plug in 1, plug in 0. Okay, 3 over 2. 3 over 2, flip it with 2 over 3. 2 over 3, 3 cancel out, it's a 2. 3 over 2 is 5 over 2, so it's a 2 over 5. 1/3. Alright, just coefficients simplified a little bit, and then we plug in upper limit 1 for x, lower limit is 0 for x. When 1 plug in, each every power of x becomes a 1, so it's a 2 minus 3 over 2 minus 2 over 5 plus 1/3. When 0 is plugged in, everything turns 0, so it's 0. So this be the volume of the solid or revolution in this problem. Alright,